Hi, welcome to the video lecture for Chapter 2. We're going to be covering frequency distributions. So let's get started with what is a frequency distribution. So basically, a frequency distribution is a summary for data which individuals are located in categories. It could be in the form of a table or a graph. So when we have categories, is what it is categories on one area. Let's say if we're using the table, categories in one column, and then frequencies of those categories in the next column. So basically, the frequencies are the number of individuals or the number of observations for that specific category, specific score, or a range of scores. So this is a way that we can organize, especially large data sets, where if I just throw out a bunch of numbers, it doesn't make a lot of sense. But if I can organize them into a frequency distribution, it'll make much more sense for the consumer. So here is an example of a simple frequency distribution. So we have our categories on the left column, and then the frequencies of those observations in the right column. So if you could see X, that's our variable, and then F is the frequency that those occur. So in this case, people could score 1 through 5. Let's just say how many people are in your household. Can't have zero. If you have to have at least one person in your household. Let's just say the question was how many people are in your household. So 3 people said they only have one person in their household. 7 people said they have 2 people in their household. 3 people said there's 3 people in their household. 2 people said that there's 4 people in their household, and one person said there's 5 people in that household. So this kind of gives you an idea. You have to be aware, you can kind of see the patterns. The majority of people in this sample of data said that they had 2 people living in their household. So the frequency is the number of observations, where that X on the left-hand side of the column is the potential scores or the categories within that column. Now, for psychology or social behavioral sciences, frequency distributions, when we're talking about tables, this is a table, always start lowest at the bottom and go high to the top. So we never ever start low at the top and go high to the bottom. And we always start counting when we're creating these from the bottom and then going to the highest number. So this is where you can start seeing those notations and calculations starting to play into our statistical knowledge at this point. So if you'll notice here, it talks about to compute the sum of X from the table. Remember that summation symbol, which looks like an E, summation, is the same thing as saying add. Is what that's saying is add all the X values. But the problem is if you just looked at this table and you said, oh, okay, I'll add the X values, and you went 5 plus 4 plus 3 plus 2 plus 1, that wouldn't account for how many of each of those there are. And so you would end up having what 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. The sum of X is not actually 15 because we actually have to account for the fact that there is only one person scored 5, but 2 people scored 4, 3 people scored 3, 7 people scored, 2. So in that case is what you need to do is multiply across. That's where you would do F times X. So you do 5 times 1, that's 5, 2 times 4, that's 8, 3 times 3 is 9, 2 times 7 is 14. 1 times 3 is 3. And that once you get those F times X scores, then you can add those so that you can have the actual sum of X. And there is a video on this in the order of opera or the using a frequency distribution table to calculate. There's a separate video that goes through those calculations. Right now, I'm just introducing you what's happening, what a frequency table is, what the distributions are. Those calculation videos are separate little videos. I just kind of walk through this verbally in these lecture videos. So let's take a look at how this frequency distribution is converted. So in this case, we asked parents the number of children that they have. They're all parents. So, and it's the same data in reality, but it could be different things. But so we only asked people who are parents at what their number of children that they have is. And so here's like the actual data set that says number of children. When you see that, it's kind of a lot of data of raw scores. It's hard to really kind of make sense of it. This is actually a small set of data, but in reality, we we often are dealing with sample sizes of 30, 40, much larger sample sizes. So it gets more complicated to understand a raw data set without organizing it in some way. So when we convert that to a simple frequency distribution, you can see on the right, that frequency distribution, you see X in one column, F in the other. That F means those numbers below that are the frequencies of the scores that are corresponding scores. So here's where you start learning some new notations, some of those notations. So you might not be able to see it. I can't see it on my screen for some reason, but capital N is the total number of observations in a population. A lowercase n, a small n, is the total of number of observations in a sample. And I went over this briefly in chapter 1 as well. So if I was to say, well, what is the sample size for this data set of number of children? That's where you're going to add up that frequency column because that's how many observations there are. That would be your sample size added together. So, 3 plus 7 is 10, plus 3 is 13, plus 2 is 15, plus 1 is 16. So the sample size is 16. So I would report that lowercase n equals 16 if I was asking what the sample size is. So it's a way that you can simplify that data. And if you'll notice over here in the raw scores, there's 4 in each column, right? And there's 4 columns, that's 16 scores. So it should match. The raw scores, the number of raw scores you have should match with the sum of that frequency column. It should equal that. So that's a simple frequency distribution. Those are like very frequently used for small data sets with a small range of numbers, meaning there isn't a drastic difference between the lowest number and the highest number. It's a small window of possibilities. So when we have a frequency distribution, often is what we do is convert frequency distribution, or we use frequency distribution tables to report more than just basic, here's the possible scores, here's the frequency of those scores. We often is what we do is we want to convert and start looking at proportions and percentages of those observations or those scores. So proportion is the notation of a lowercase p. It is basically a fraction of the observations out of the total number of scores possible, or out of the total sample size. So even though it's calculated as a fraction, so for example, if I said, what is the proportion of people that scored 4 or said they have 4 children? Well, 2 people scored 4 or said that they had 4 children. So your um, fraction would be 2 divided by 16 because 16 is the sample size or population size, the total number of people that participated. So if you divided 2 um, by 16, you would get 0.125. And that's what you would report. We never ever report proportion as a fraction. And it can only be between 0 and 1. You can't have more than 1, and you can't have less than 0 because it's not meaningful. So 0.2 or 0.125 is the proportion of people that have 4 children. And as you notice, it goes up. So for the proportion of people that said they had 2 children, that's 0.4375. That's a lot, much larger proportion. So when you start looking at these, they start making much more sense. What seems probably more meaningful is percentage. So that's that fourth column is where we convert to percentages. It's actually very easy to convert to percentage because if you just take that proportion, move the decimal over 2 places to the right. So the actual equation is P times 100, which is P times the proportion, which is the same thing as you get your proportion, which you should already get in that third column, move the decimal over 2 places to the right. So if you'll notice, for those that said they have 5 children, only one person said they had 5 children. That's 1 person out of 16, which is a proportion of 0.0625. The actual percentage is 6.25%. And often is what we do with this percentage column. I left this to 2 decimals because that's the most common reporting that for our class when you report the final calculation. But it is perfectly fine to round to a whole number for percentages. So it would be perfectly fine for you to report 6% for those who have 5 children, 13% for those who scored or said they had 4 children because 12.5 rounds up. 19% for those who reported 3 children, 44% for those who reported 2 children, and 19% for those who reported only 1 child. So it's kind of how we create that frequency distribution table. So let's kind of look at when we would use a grouped frequency distribution table. So it's just a simple frequency distribution table when we have categories with frequencies and their whole numbers with frequencies. But when we have large ranges of numbers, or we have numbers that include decimals or fractional numbers, we'll often create grouped data. And it basically means that we're taking a set of scores and we're creating intervals where the frequency of each score can fall within an interval, which is a range of numbers. So an interval is a range of values which the scores fall between. So let's look at what this looks like. So here is a grouped frequency distribution table. Here's our scores. We have raw quiz scores. This is what the original data is on that left side. This is just raw data. Someone scored 10, someone scored 8, but if you'll notice, 2 people scored 7. So there's more than one, but they are organized to help kind of see that transition. It looks like no one scored 0. But 0 should always be included, especially if 0 was a possibility. And I always say include 0 just to be safe, because even on the last here, if we included 0 here, it would just be 0 and 0, 0, 0 across the entire bottom, and that would be fine. I would prefer that over you um, making a judgment call of not including 0 and it being incorrect. It's always better to include the 0. So is what we've done is we've created a grouped frequency distribution table. Now, often is we wouldn't, you know, a difference between 1 and 10 or 0 and 10 is wide enough to where we might want to go ahead and use a grouped frequency distribution, just because that's a lot, unless we have large data sets. But it's often a wide enough range to where it might make it more simple to be able to kind of simplify that data, be real quick and easy to look at, see what the patterns are. So let's look at this grouped frequency distribution table. So basically X, this is on the left-hand side where it says quiz scores, that's X. That's our possible scores. And then F, the lowercase f, is that column on the right. Those are the frequency of those scores. So you could use the full term or the notations either way, but this helps break things down for you. The intervals, when we say intervals, those are basically the rows. So you can see there's 4 rows or 4 intervals. And the width of each of those intervals is 3. So now I know this sounds kind of odd because it's like, wait a minute, 2 minus 0 is 2, 5 minus 3 is 2. We have to remember that we need to include the upper and lower boundaries. So 0 is part of that and 2 is part of that. And in actuality, the range for 2 is all the way up to 2.5. And then the range, for let's say 3 is all the way below down to 2.5. So basically 2 butts up to 3 because this is what we would consider continuous data or quantitative data where there's possibilities. So I always say if you're trying to figure out your width, use your fingers. Don't even worry. Don't go 2 minus 0 because that won't be correct. 0, 1, 2. That's a width of 3. It's okay to use your fingers in this class. If you have to use your toes, I don't care. As long as you're coming up with the right answers, that's fine. But sometimes that's the easiest way to come up with your width. Or you could do, the highest number minus the lowest number and then add 1. That will always work out too because you're including the 0.5 below and the 0.5 above, which is added together is 1. And so just like before, the frequencies are on the right. So 5 people scored between 6 and 8 on this quiz. So it's very meaningful in that sense. So as you can see, if we add these up, n equals 10. And this capital N is suggesting that this is a population. Even though usually populations are huge, that capital N is suggesting a population. So let's talk about how we would come up with the grouped frequency distribution table. And these are just some little hints. Intervals, think number of rows. Width, think the number of possible scores included within the interval. And then the sample size or population size is just by adding up those frequencies. So let's learn how to calculate or create a grouped frequency distribution table. So first and foremost, like if you have a data set and you're asked, create a grouped frequency distribution table, use these steps. Just automatically in this class, use these steps, okay? Otherwise, it's a guessing game. And you're probably having to recreate a table over and over and over again. But for this class, I feel like it makes it very simple for you to just follow these steps. So is what you're going to want to do in step 1 is find the real range. So the real range is the difference between the largest number and the smallest number. okay? But that's just the range, the largest minus the smallest. If you want the real range, you're going to add +1. That +1 is including the lower boundary and the upper boundary, the 0.05 or the 0.50 below and the 0.50 above. So the largest number minus the smallest number +1, you find that real range. So then you're going to want to take that real range to find out what your interval width is, meaning how many numbers are you going to include in each of your intervals. So is what you're going to want to do is take that real range that you just calculated and divide it by the number of intervals that you would like. For this class, I always say divide by 10. I always give you data sets that fit 10 intervals perfectly, unless I tell you otherwise. So if I was to tell you otherwise, I would say create a grouped frequency distribution table using 5 intervals. So instead of dividing by 10, you would divide by 5. But if I don't say anything, you would divide your real range by 10, and then you would round that to a whole number. And remember, when we're rounding, if let's say you get the number 5.4, that rounds to 5. But if you get 5.5, that rounds to 6. So anything 0.5 and higher, round up. Anything 0.4 or lower, you round down. So make sure that you're really careful about that. And then once you find out your width, you can start calculating, you can start creating your frequency distribution table, starting at the bottom of the table, including 0, with the values increasing. So let's look at how this would look like. So here is a large data set, as you can see. There's 50 introductory statistics students. That's a lot of numbers. So sometimes it takes a little, you want to be really careful, like when you're checking off, like, making sure that you have the right sample size, making sure you have the right amount of people within your intervals. So in this case, when we did our real range, the highest number is 100. So sometimes that's a hard part too. It's going through and finding what's the highest number and what's the lowest number. You might want to double check that a couple of times because it's easy to miss a number. So in this case, the highest number is 100, the lowest number is 7, and then we're going to add 1 for that to make it the real range. So that real range is 94. So then we're going to want to find the width. So we're going to divide 94 by 10. And as you can see, we get 9.4. We're going to round that to 9. So because 4 is less, being 0.4 is less than 0.5. So you're going to round down instead of up. So our width is going to be 9. That means we're going to include a range of 9 for each row or each interval. So here's what that would look like. And I'm sorry, my face is right in the way. Let's move this over here. Whenever we do a grouped frequency distribution, we always include the columns for proportion and percentage. But as you'll notice, our lowest number was 7. So is what I do is when there's a gap between 0 and the lowest number, I always start on that second row basically with the lowest number, and I start counting there. And then the bottom row or the bottom interval, I put 0 to the number right below the lowest number that is observed. So if you could see in parentheses, I have 0 to 6, and I have zeros straight across. That's because no one scored between 0 and 6, and 0 and 6 is not a width of 9. So it's a different width. That's the only time you can have a different width. And so is what I did is I started counting at 7. So if you look, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's 9 fingers are being held up. It's really hard for you to see, probably 9 fingers. So that's 7 to 15. Makes it pretty easy. One thing that I always say is an easy one is, okay, you have 7 to 15 in that first row or first interval. write 16 in the next one, and then just add your width to the highest number in the interval below. So I would do 15 plus 9, and that would be 24. That would be the number, the highest, the high range of the next interval. So if you'll notice, each interval has 9 um, numbers included, and each interval is even. They each have a width of 9, except for that bottom interval where we included 0 and we have those parentheses. So then we can start getting those frequencies, and that's where it gets a little complicated because you have to go through and count, okay, how many people scored between 88 and 96? And if you remember, this original data is pretty cumbersome. So often is what I do is I use like a highlighter and I highlight, with different colors, or I use, you know, uh, check marks or things, but I wouldn't totally scratch things out because it's very possible you might be scratching out the wrong number. And then it's hard to go back and see. And this will make more sense when you practice. So when you get your frequencies, if you remember, this had 50 observations, 50, a sample or population size of 50. When we add up this frequency column, that should equal 50. And I always, especially in grouped frequency distributions, recommend add that up before you start moving on to doing your proportions and percentages. Because if you don't add up to 50, you've missed a number or you have counted a number twice or something, which is very easy to do. Then you have that proportion column again. So at the very top, 5 people scored between 97 and 105. So there was 50 people total. 5 divided by 50 is 0.10, and that's your proportion. And then you move the decimal over 2 places to the right, and that's 10%. And if you notice in this one, I showed you the example of where I kept these at whole numbers. So remember the grouped frequency distribution. You want to include a 0 at the bottom, even if no one scored 0. And same with the simple frequency distribution if 0 was possible, but definitely with a grouped frequency distribution. And you always want to start counting at the lowest number. And if the lowest number is not 0, then put that in the second interval or the second row and start counting there. And then include that 0 in the interval at the very bottom. Sounds complicated. Again, there is a separate video, a short video that walks through how to do this. So it might be good for you to go through that and walk through that, where I use a whiteboard and help you a little bit more hands-on with that one. So let's take a look at how these tables, these frequency distribution tables, are useful in converting to other types of summaries of data. And is what we do is we often take distribution tables and convert them to graphs. And so one of the things that we often use are histograms. And histograms displays the frequency of continuous data, meaning you can have decimals, you can have a fraction of numbers, so there's any possible amount of numbers in between. Now, when you get data, often it's in whole numbers, like we'll present data in whole numbers. But if there was a possibility originally of there being decimals, it should be a histogram. The only time, so just because you see whole numbers doesn't mean that that's all that you can get. So want to be very careful about that. So with a histogram, your horizontal axis, that bottom axis is the x-axis, that basically tells us the potential scores, okay? The potential scores that you obtain. And then you have the vertical axis, the y-axis, that tells us the frequency of those scores on the x-axis. And the frequency is represented by a bar. So a bar being kind of this rectangle that shows us the frequency of scores. If there is no bar, then there was no frequencies. So With histograms, the bars are touching to show that there is a possibility of data between whole numbers. So it's telling us that it's continuous data, and those bars are touching, which signifies those upper and lower boundaries. So let's take a look at what this would look like. So as you can see here, we have exam scores. This is the histogram for that. So if you'll notice, those exam scores way back here, they were all in whole numbers. But most of the time you can get like 89.2%, 89.5%. These are all rounded to whole numbers. It is originally continuous data, so we're using a histogram, and those bars touch to tell us that there could be any possible number in between those bars. So basically, if you'll notice, like, let's say from 88 to 96, the lowest bar in the middle between the interval below starts at 87.5. And then the upper boundary ends at 96.5. It's not easy to see on this, but that is the reality of it. And so then when you look across, you can see, okay, 88 to 96 was most frequent. And the majority of people kind of scored at this high end, and then less and less people scored lower and lower and lower, right? So it helps give us a visual of what's going on. So with histograms, it's for continuous data. Bars touch to show that that data is continuous. Other types of distributions for continuous data would be polygons. Polygons, you have used the term line graph. That's not the technical term. The technical term is a polygon. It's a dot and line graph. And it's used in the same exact manner as a histogram, except for now your dot has to line up in the middle of your interval, basically. So if you use that bottom interval, the lowest number is 0, the highest number is 2, right? 0 to 2. And you would do 0 plus 2 and then divide it by 2, and that splits it right in half. And that is where your dot would go, your data point for the frequency of two scores. Which would be 1. And I'll show you what that looks like. So here we have time in months. If you'll notice, we have a score of 0. There's no one. But right here, the dot is at 1. Here we have a dot at 4 for, it looks like maybe 11 people was within that range. It could look like this on the x-axis, or you technically could have the grouped intervals as well. So in reality, often is what we see is instead of it just being a straight up 0, 1, 2, we'll actually have 0 to 2 at the bottom, and then we would have the next interval, the next interval. That is very frequently done, but you can see it done just straightforward with the values at the bottom as well. And so it's just a method of utilizing a different type of graph for continuous data. Now, typically I use polygons when I'm comparing two different variables. So maybe I'm looking at time in months between men versus women. Then I have two lines, and it can show the patterns and the differences between the two variables. That's usually when I use a polygon. And I rarely have you use polygons in this class, but you should be able to recognize them and still read them. So to see. So as you can see, time in months, a score of 10 was the highest frequency, or in that range of 10, and there was more than 50. It looks like maybe 55 people basically scored within that range. So you should be able to kind of read it in the most simplistic manner. The next one that you're kind of distribution that you'll see is with a bar chart. And a bar chart is used for categorical or discrete data. So it just tells us the frequency of categories. And again, that horizontal x-axis shows us the potential scores or categories. And that vertical axis tells us the frequency, and the bars just represent those frequencies for each of the categories. Now, with bar charts, the bars do not touch. They absolutely don't touch. There's a space between bars, and that tells us that there's no potential for values between the whole units, the whole numbers, or those categories. Okay? So in this case, the number of days absent. Absent means you've missed an entire class. Doesn't mean you're tardy, you missed an entire class, okay? So you can't have, I missed 1.5 days. There's no such thing. So they're whole numbers. So, in this case, 5 people missed 0 days. 5 people missed 1 day. 3 people missed 2 days. Or, I mean, yeah, 3 people missed 2 days and only one person missed 3 days. No one missed 4 days. So those spaces between the bars tell us there is no fractional values in between. There is no decimal values in between the whole units. So it's very important to be able to distinguish between a bar graph and a histogram. Mostly a bar graph would be for discrete data. A histogram is for continuous data, and they look very similar, except for histograms, the bars touch. With a bar graph, the bars are separated by a space. Lastly, you can use pie charts for discrete data. And so pie charts are kind of this circular graph. I'm sure you've seen them before. We often use this when we're talking about kind of data, like some kind of data that describes populations in some sense, like kind of a demographic information. So in this case, um, each sector or slice is relative to a percent or a proportion. Okay. So in this case, we have class modality. 48 people were in person modality, which was 28%. So if you can see down here, in person is the yellow. So this yellow slice represents the in person. Hybrid is the gray. That was 35 people. And so each slice represents a proportion or a percent. And so the entire pie is 100%, basically. 100% of the um, sample size or 100% of the population size of observations. Then one tip that I have is when you create a pie chart, be very careful about pie charts because when you use colors that are muted or similar, it might look great on your small screen, but if you project it onto a large screen, sometimes those colors are very hard to distinguish. You also need to be very conscious that some people are colorblind, so they might not be able to tell the color differences. Some people see green and gray is the same color. My husband is one of them. He can't tell the difference between green and gray if they're close to each other. So those are things that you want to be aware of. Maybe using very bold colors, very bold differences, like light and dark differences, or even use patterns. I mean, you can take a slice and make it a checkerboard, and you can take another slice and make it snowflakes or something. So there's lots of ways to be able to do a polygon so that you're including everyone and not making it difficult for some people to read it. So it's just a little tip. I rarely have you do, did I say polygon? I'm sorry, I meant pie chart. I rarely do pie charts in this class. Just because they're really time consuming to create on the software. But you never know, I might feel excited about it on some material in the class, and I might have you create one, but I would always walk you through the steps in some way, shape, or form. And for you, it would be usually hand drawn. You could do it on software as well, depending upon the assignment. But kind of a fun approach, very seldom used in social behavioral sciences unless we're just talking about demographic information. So some important things like I kind of covered it about those pie charts. Again, I'm kind of hiding some of the information here. Colors that are highly contrasting, they're not appropriate to use a really large number of categories. Like say you have 20 different categories, it's inappropriate to use, or if you're only using two categories. Usually you want to do like anywhere between like um, three and maybe five categories is usually what we'd be looking at. And if you have really, really small sample size or population size, it's usually not appropriate for that either. So it's usually when we have large amounts of data and that are split up into a handful of categories in general. So some tips about using pie charts. And it helps you to recognize when people are using these things inappropriately too. That's the whole point of this. It's not for you to just be able to go out in the world and create graphs willy-nilly, which is fun, but it's also for you to recognize when people are presenting graphs to you or presenting data to you in an inappropriate way. I'd love for you to be able to start recognizing those things. So hopefully this summed up chapter 2 for you. If you have any questions, please do not hesitate to email me. I am here for any questions, and there are lots and lots of supplemental videos and resources for you that I have created on any specific topic within chapter 2.